So first of all, as I told you, I have f, which is 4x squared plus 6y squared. Then I have g, which is x squared, 2y squared, 4z squared equal negative 40. Compute the gradient vector. So this is what I'm telling you about. I'm differentiating the first function, which is gonna be an a of x. Then I will have 12y. And for the gradient vector, for the condition, it's gonna be a 2 of an x, 4 of a y, plus 8 of a z. Then I will equate each other multiplying by lambda. So this is gonna be the case. This is the gradient vector of f, which equal to lambda times the gradient vector of g. So all I have to do is to have 8 of x, which equal to lambda times 2x, 12y, which equal to lambda times 4 of y, 12y, lambda 4 of y, and 0 equal to lambda times dot 8 of z, and that's the condition that I will need to be sure that it doesn't contradict anything, as you can see. The coming step is to, from third equation, try, this is the, from my point of view, this is the step that you will need to stop and think. Okay, I will need to look to the simplest cases that I have for the simplest equation. I believe the third one is really very obvious. You have 0 equal to lambda dot z, which means you have two alternatives. Either lambda is equal to 0 or z is equal to 0. So from this from the third equation, you will have these two cases. Lambda is equal to 0 or z is equal to 0. If lambda is equal to 0 and z doesn't equal to 0, I will use this information and substitute in the first two equations. If lambda is equal to 0, this will lead to x is equal to 0 and y equal to 0. I will take the three conditions. X equal to 0, y equal to 0, but z doesn't equal to 0. And all of them equal to 40. From the third equation, I will get the value of z. So once more, as I told you, then the constraints becomes take x equal to 0, y equal to 0, and start substituting. Then you will have your z positive or negative root of 10. Those are how many points? 2 points. Keep them with you. Then I will start the second case. The second case, it is the case of having z equal to 0. Okay, and the lambda doesn't equal to 0. So critical points, I have them now. I have 2 points of them. If you want to evaluate the value of f at these 2 points, z equal to 0. Just keep it with you. Then I will go to case number 2. That's z is equal to 0. If you put z equal to 0, okay, in the third equation, you will have x squared plus 2y squared equal to 40. And you have these two conditions also. So then the constraint becomes, at this case, x squared plus 2y squared equal to 40. I will start using the upper equations, which states from the Lagrange multipliers, you have 8 of x equal to lambda 2x, which means lambda is equal to 4 if x doesn't equal to 0. Okay, that's the probable value of lambda. Then once more, I will take this value and substitute, so it's going to be 12y, which equal to lambda dot 4 of y. Lambda is equal to 3 if y doesn't equal to 0. Now you have a consistency of lambda is equal to 4 to 3, which is a contradiction. So I will reject this case. I will go either x is equal to 0 or y is equal to 0. Any other case of these two cases. So I will start with x doesn't equal to 0. If you substitute nada in this equation, ya Farid, which is really very important, these steps are important. If I substitute in this condition, x is equal to 0, then you will have y squared equal to 20, which means y is equal to positive or negative the root of 20. If I consider the second case, which is y is equal to 0, and substituted in here, you will have x squared equal to 40, which means another 2 points. This is the discussion in the next step. So I'm studying the case at z equal to 0, and if x is equal to 0 and y equal to 0, making the substitution exactly as I described for you. So you will have 2 points, where x 0, y 0. X 0 and z equal to 0, but y is positive or negative 20. As you can see, and substitution will leave you with 120. This is the case of having y equal to 0 and just only x is positive or negative 40. How many points do I have at the time being? 6 of them. So I have 6 points. I had 2 when z is equal to 0, okay? Then I had another 2 while x is equal to 0 and z equal to 0, and the general case. Also, this is going to leave you with 160. So the possible critical points, this is 0, 0, positive or negative 10, 0, positive or negative 20 and 0, and positive or negative 40, 0 and 0, 0, 120, this is the minimum, that's the maximum point as you can see. It's really very simple using Lagrange multipliers as you can see from these problems. Once more, steps to find absolute extrema of a two-variable function of x or y, summary of root chart, check the domain, get f of x, f of y equal to zeros, use the second derivative test, analyze the boundary, parameterize or Lagrange in order to find your case if it is a global maximum or global minimum. Those are the many steps that I told you about previously. Steps to find the absolute extrema of a two-variable function. Also, I did go through the details, and this details in the case of unconstrained optimality. This is the part that I started my lecture with, okay? So, determine the domain, identify if it is open or closed, because Whiskers states, this is before you came, Nada and Farid, okay? If you have a compact interior or a compact domain, then you must find, or there is exist for sure, an extreme point. But if it is open, no. I'm talking about absolute or global maximum or minimum. But probably you will have local maximum or minimum if the function contains this. Yep, that's the Wester's theory. In case of unbounded or open domain, extremes may exist or may not, but if they exist, it will be an interior point. Find the critical for the interior of a domain. Same steps as I explained previously. This is using the steps of the Hessian. I really did go through this at the beginning of our lecture today. If you need to parameterize your domain in order to make it easier you solving, you can use parameterization or use Lagrange to evaluate at certain curve, which means I will get the gradient vector of the function and the gradient vector of the constraint, equating them both together and solving the system of equation as we did in the previous problems. I believe compare all values to determine absolute extrema. That's the continuation of what we did. These are the steps of absolute, put to you as steps and also as a flow chart. I believe I shared this PDF with you. I'm not really sure, just check your WhatsApp if I shared this PDF or not yet, okay? So, but I think I shared it, okay? This problem is really very nice, a very important problem, okay? Because it's an example even of modelization or modeling your problem. We will determine the points on the sphere x squared, y squared, z squared equal to 36. So I need to determine the points on this sphere that are closest and the farthest apart from the given point, from the point 1, 2, 2. So once more, if you measure, I have a sphere and I have a point. I need to find the points on the sphere that's closest to 1, 2, 2 or farthest to 1, 2, 2. Do you understand what I'm saying? Okay, how to do this? The good idea in this problem that I will formulate my function. I will formulate my function. What's required to be optimized? What's the required to be optimized here? The distance between a point and 1, 2, 2. Am I right? Do you remember the equation of the distance, which is x minus 1 to the power of 2 plus y minus 2 to the power of 2, z minus 2 to the power of 2 under square root. But if I use the square root formula for this distance and I'm trying to maximize it or minimize it, the calculus is not going to be easy. See how to manipulate this relation in this problem. It's really very nice problem. So the first step that I will do, ask it to find the point on the sphere, blah, blah, blah. Okay, which is nearest or farthest from the point 1, 2. I will define the objective function. My objective function here, it will be the distance between any point and 1, 2. So my equation will be the square root, which is the distance of x minus 1 to the power of 2, y minus 2 to the power of 2, z minus 2 to the power of 2. But in order to make your life easier, instead of maximizing or minimizing the square root of the distance, I will neglect the square root. The square of the distance is going to be the same. Am I right? But it will make your life easier in differentiating or dealing with a gradient vector. Because by the end of the day, this problem now become, I need to maximize or minimize this function, but subject to what? To the points on this constraint. So now I formulated, this is the function to be optimized, but subject to this constraint. The constraint states that x squared plus y squared plus z squared minus 36 equal to 0. So I have my equation that I want to optimize, okay, and subject to the sphere equation. What's the next step? I'll get the gradient vector for the function to be optimized. Then I will get the gradient vector for the condition. Then I will equate each one of them together. But don't forget your Lagrange multiplier. This is what's going to happen. This is the constrained optimization problem subject to the equality constraint as I told you. So now I will use the Lagrange multiplier as been said previously. This is gradient of f equal to lambda gradient of g. Let's differentiate together. Miss Nada, I want to differentiate this part, which is going to be 2 of an x minus 1. This is for the x coordinate. Then 2 y minus 2 for the y coordinate. Then 2 z minus 2 for the third coordinate. That's the gradient vector of f. The gradient vector of x of g is going to be 2x, 2y, 2z. Here you are. Then I will equate the first component equal to 2x, but multiplying by lambda. This is the Lagrange equation. Here we go. That's the first condition, that's the second, that's the third, and this is in a simplified way trying to multiply and taking common factor, which leads to x minus 1 equal to lambda x, y minus 2 equal to lambda y, z minus 2 equal to lambda z. And don't forget, plus these equations, you will have to satisfy, this is the system that you need to solve. You will need to satisfy that x, the sphere condition, that each probable solution should satisfy the equation of the constraint. So I will start with x minus 1 equal lambda x, get it to the other side, take x as a common, you will have x 1 minus lambda is equal to 1, which leads to x is equal to 1 over 1 minus lambda. That's the first relation. The y, the z, those are the three values. Take them and substitute, okay, here's the value, plug into the constraint. Let's check if it's true or not. So I will take these values and I will start to substitute in the constraint. That's the value, the first, second, and third values. Here we go, try to simplify it in order to find the value of lambda, as you can see. And you will find that the cases is 1 minus lambda is equal to positive or negative half, which means lambda is equal to positive or negative half. I will need to study each case once lambda is equal to positive 2 or negative half. If lambda is equal to half, now I know the value of lambda. Once I knew the value of lambda, Miss Nada, what to do? Now I knew the value of lambda, what to do? I will take this value and then I will plug it back into x, y, and z. Am I right? Then you will be able to get your values. Case number 2, lambda is equal to, try to solve. This is 1 minus lambda equal to negative 1 over 2, which means lambda is equal to 3 over 2. So this is the first case. That's the second case. I will take each one of them and substitute in x, y, and z, because both of these two cases are identified for the time being. So this is half, just to plug them into the expressions for x, y, and z. You have now the value, the point is 244. In a similar manner, take the value of 244 and substitute in the distance. Should I give the distance, the square of the distance, which is x minus 1, blah, blah, blah. The first equation. Okay. Then do exactly the same, but with lambdas equal to 3 over 2. I will take these equations and plug them also in x, y, and z. This is for the x, that's for y, and that's for z. Then I will have the probable point, which is -2, -4, and -4. Now, determine the closest and the farthest. Take these 2 points and substitute in the distance. That's the equation that we are going to substitute in. That's what I'm telling you about. That's the square of the distance between the points on the sphere and 1, double 2. Okay? Start substituting. You will have, with the first one, d is equal to 3. The second one, I believe, d is gonna equal to 9, as you can see. So this is the value of the substitution. Take square root, 3. 81, take square root, which is 9. So this is the case of the farthest, and that's the nearest point on your sphere. The beauty of this problem, it's really very simple, but in this problem, he show you how to model your function, how to find the function to be optimized. Constrained with a certain condition, okay? So once more, this is the sphere. These are the points nearest and the farthest from 1, double 2, as you can see, and this is the remaining of this problem. In this one too, he wants you to calculate, if they exist, the extremes, relative and the absolute, of the function d that maps stuff from R2 into R, which is a function in several variables, given that f of xy is x squared plus xy plus y squared, when the domain is R2 and the domain is y is less than or equal to x, and the x is less than or equal to 0 and the less than or equal to 1, and y is greater than or equal to 0. That's the description of the domain. Miss Fatin, why he gave you the domain in details? Because he needs you to find an optimal solution inside the interior and extreme point. And this is why your domain should be compact. Closed, it will make a difference. If it is compact, then you will have absolute values. If it is not compact, then you will have the interior points, and that's it. Okay, D is the set of points that satisfy the equation x squared y squared equal to 1. So the first is D is equal to R squared. In this case, I will try to find the local critical points, which means I will go grab the gradient vector, put the gradient vector equal to 0, because it's an unconstrained optimality. معايا Mr. Farid? Okay, in this case, I will try to solve this system. Y is equal to -2 of an x. Then into the second step, or the second derivative, substituting, now I have the critical point. Now x node is equal to 0 and 0. I will get the Hessian matrix, which means I will differentiate the first derivative second time for x, the second derivative second time of y, and the mixed derivatives. This is the Hessian matrix. Mr. Ziad, evaluate the Hessian matrix. It's going to be 4 minus 1, which is positive 3. Please try to find the value of double x. The value of double x, which is 2x. This is the value that I have for f double x. What is f double x? Double x is 2. So the value of the determinant is 3, and the f double x is 2. This is a minimum point. So continuing, this is the Hessian matrix. That's D, as I told you, it's 3. F double x is 2. Then this is a local point, and also a global, or the local point, which is minimum value at 0 and 0. That's the identification of the local point. For the first case, I didn't identify the domain. The domain is open. I'm talking about optimizing, but the domain of the functions are 2. Am I right? In this case, you don't have an extremum. You have a local points, and these local points, in between them, you will have your global optimization. معايا? Because if you have, for this problem, you don't have a global maximum, but you have a global minimum, which is the lowest point that exists. Okay, if I'm studying, as I told you, if I'm studying the case, in this case, which is 2, in this case, the study will be different, Ms. Fatil, because I've already determined the domain. The domain is not R2. I will study the optimality, but under the condition. The domain is what's given Farid. The domain is given y is less than or equal to x. So if I'm in 2 dimension, y is equal to x is just the 45 line. But y is greater than x as this, y is less than or equal to x. It means the lower triangle of your y and x. What I mean, guys, from this relation, this is the x and y. This is y equal to x. This is the region that I'm talking about. This is satisfying the first inequality. The second inequality, Ms. Fatil, states that use only the values of x that's greater than 0 but less than or equal to 1. So I'm really interested in those values, from 0 up to 1. The third is stating that just only for the values where I is greater than or equal to 1. So those are the boundaries of your domain. Are you with me, Ms. Fatil? These are the domains. So now you have a compact domain. Not all are 2, no. You are talking about the region which is blue y equal to x, above y, above the x-axis, and until x is equal to positive 1. I need to find the extremum points belongs to this domain. Now I can find extreme minimum, extreme maximum, okay? Okay, so it's really, this problem is taking everything that we stated in this lecture and in the previous one. So once more, this is gonna be a closed area. This is the area that we talk about. So I will start x squared xy equal to y squared. We already, from the previous steps, we found that we have a global minimum at the origin sub. Okay, from what we did, now I have the global points. I need to search for the extremum. Okay, the absolute points. The absolute points will happen on the boundaries. So I will need to discuss the boundary issue. So once more, if W0 is equal to 0, evaluate on the boundary. As I told you, let's consider the 3 edges. The first edge is x equal to 0, and y belongs to 0 and 0. Single point is 0 and 0. Edge number 2, which will happen at x equal to 1. That's the edge that I'm working with. And y is equal to, since x is equal to 1, y is equal to 1. So the point 0 and 1. Once you substitute with this relation, okay, you will have y squared plus y plus 1. Okay, minimum, this value will be minimum when y is equal to 0, and maximum when y is equal to 1, and it will equal to 3. So these are the value of the function at the edge between 1 and 3. In a similar manner, if y is equal to x, I have the x equal to, belongs to 0 and 1. So if you make the substitution y is equal to x in your function, once more, this is gonna be the result. Substituting by the beginning of the domain at x is equal to 0, then f is equal to 0. If x is equal to 1, then it's gonna be equal to 3. Now I identified the points or the maximum and minimum. So according to this remark, that 0 is the absolute minimum, and at 1 and 1, this is gonna be the absolute maximum. In this discussion, I found the extremum or the absolute maximum and the absolute minimum because the region is compact. Okay, the third case, this is case number 3. Case number 3, I need to optimize x squared plus مش عارف ايه xy plus y squared. But in this case, Farid, I have a condition. I need to find the optimality, but under the condition, it is one of the points of the circle, unit circle, which is x squared plus y squared equal to 1. I'm using Lagrange in this problem. So I will start, use the unit circle, Lagrange multiplier, which means I will find the gradient vector of f and get the gradient vector of the constraint, and I will, from both of them, I will equate them. These are the two equations that I will be dealing with, and I will substitute in the constraint. If I consider x equal to 0, y is going to be equal to 0. But if x and y is equal to zeros, this is not going to satisfy the equation. So this point can't be a critical point. So I will go to the case of y is equal to 0. Once you put y is equal to 0 in any of the equations, substitute in these equations, you will have 2x equal to lambda, 2x which means lambda is equal to 1. Then continue, check constraints, x squared is equal to 1, which means it will happen when x is positive or negative 1, as I told you. When x is positive 1 and y is equal to 0, the value of the function is going to equal to 1, and for negative 1 is equal to 1 also. Now for the case of x doesn't equal to 0, y doesn't equal to 0, in this case, okay, try, as I told you, to substitute from these two equations in each other. You will have 2x plus y equal to lambda times 2x, which means lambda will equal to 2x plus y over 2x. Take the value, okay, take the value of lambda, and then start substituting for these two values from these two equations, equate them together, make a cross multiplication. I'm trying the best that I can in order to find a solution. Then you will have x squared plus 2 over xy, which leads to y squared is equal to x squared, which means either y is equal to x or y is equal to negative of x. Those 2 points to happen, if y is equal to x, then you will have x is equal to half and half, am I right? Yes, 1 over root 2, and y is equal to positive or negative 1 over root 2. Now I found a minimum point, a maximum point which will happen, or a value of a function at 1 and 0 and 0 and negative 1 and 0, then I will go through these points. Also, those are the probable points. The lowest of them is the minimum and the largest and the maximum. This is the outcome of the substitution using 1 over root 2 and negative if they have the same sign, if they have opposite signs, according to this relation. If x is equal to y, or if x is equal to negative y. If x is 1 over root 2 positive or negative, then y will be the same sign or the opposite signs. This is why we have 4 points. All of them, the value of the function is 3 over 2. Okay? So for the time being, the lowest point or the lowest values will happen when you substitute and is equal to 1, and the largest is will happen at these 4 points. As you can see, this problem analyzed the 3 possible cases. If the domain is not compounded, it's not compact, it's an open domain. If the domain is compact by a certain region, the case number 3, if you are studying your optimality and you have a constraint, okay, which is like this unit circle that we saw in the last one. Thank you very much for our lecture today. By the end of this lecture, we concluded the first part of our course, and starting from next Monday, I will go to integration. We will study the multiple integration, the double integration, then the triple integration with all various, with all theories, the line integration, the Green's theory, the integration on the contour, the integration on closed curve. All of this will be covered, and also in multiple dimension. And we will use the advantages of either parametrization or changing the coordinates from Cartesian into spherical or from Cartesian into cylindrical coordinates. So most of the stuff that we studied previously will work within the next, as tools in the next part of our course. Are you with me? Inshallah, I will see you next time. Thank you very much.